A new traveler has slipped into the sun's domain, a wanderer from between the stars that will not be captured and will not return. Astronomers call it the third interstellar visitor, nicknamed Atlas. Its path is hyperbolic, the celestial signature of an object born under a different sun. At first glance, you might expect a familiar comet, a hazy coma, a tail streaming away from sunlight. Instead, Atlas behaves like a riddle. Hints of an odd, almost contradictory tail, flickers in its glow, and whispers about unusual chemistry suggest a body shaped by conditions far from our own planetary nursery. We have met such visitors before. The first arrived as a geometric enigma. The second looked like a classic comet carved from ancient ices. Atlas is stranger. Its light seems to tell two stories at once, one about dust and gas driven off by heat, and another about particles arranging themselves in unexpected ways. Yet there is no danger here, only an opportunity. If we listen closely, this object may describe the weather of alien birthplaces, the rules of distant disks where planets are forged, and the quiet forces that sculpt the small, cold things that roam the dark between suns. The story begins on a winter night in the southern hemisphere, when a small streak of moving light drifted across images from an automated sky patrol. The software tagged it as a possible near-Earth object, the kind of routine alert that observatories receive many times a week. Yet something about its motion refused to fit the familiar patterns. Follow-up measurements arrived from additional telescopes, each one tightening the line of best fit, and the early solution began to wobble away from a bound ellipse. What looked ordinary at first glance started to whisper of an origin beyond our sun. Astronomers searched the archives for earlier, unnoticed appearances. These pre-covery frames are time capsules, and now they yielded a few precious points of light that matched the newcomer's path. With each recovered position, the orbital arc lengthened, and the mathematics grew more confident. The curve hardened into a hyperbola, the unmistakable signature of an interstellar trajectory. Conversations in mailing lists turned urgent and careful at once. Teams refined astrometry, checked for systematic errors, and tested whether solar radiation pressure or cometary outgassing could be fooling the fit. When the data held, the news moved from murmurs to formal notice. The Minor Planet Center issued its announcement, assigning a provisional cometary designation that linked the object to the survey network that first saw it. In a handful of days, the label changed from a generic near-Earth candidate to a confirmed interstellar visitor. Observatory schedules flexed, large mirrors made room. Spectrographs were cued to listen for faint chemical fingerprints, while wide-field cameras prepared to trace the shape of the coma and the strange geometry of its tail against the crowded star fields of the southern sky. Scientists also recalibrated expectations. We had already met one interstellar puzzle shaped like a shard and another that behaved like a classical comet. This traveler looked different again. Even before it swept behind the sun, early reports hinted at odd structure and activity that defied easy categories. The community adopted a disciplined stance: celebrate the discovery, publish the uncertainties, and let the sky decide the story. A single anonymous speck had stepped out of the background, followed by a chain of human attention and patient calculation, and now bore a new name and a larger meaning. By the time the designation settled and the campaign plan took form, the narrative had flipped in a profound way. This was not a threat to be tracked for impact risk, but a messenger to be welcomed for what it could teach. Each new observation would sharpen the distance at closest approach, refine the time of perihelion, and test whether our first impressions were fair. The discovery timeline, compressed into a few intense days and nights, revealed how modern astronomy works at its best. Algorithms and archives, vigilance and verification, and the quiet thrill of realizing that a stranger has crossed our doorstep. A hyperbolic orbit is an open curve, the geometric mark of freedom. Unlike an ellipse, which closes upon itself and binds a traveler to the sun, a hyperbola has arms that never meet. The object dives inward, swings through its closest point to the sun, and then departs along a new branch that stretches toward interstellar night. In energy terms, it carries more than is needed to escape. Even at great distance, where sunlight is weak and gravity gentle, its speed remains above the threshold of capture. It is not a returning comet. It is a passerby. Trace the path backward on the dome of the sky, and it points to the southern hemisphere, rising out of star fields crowded by the Milky Way. Its approach vector lies near Sagittarius, close to the great river of starlight that hides the galactic center. That neighborhood is beautiful and difficult. The background is rich with clusters, dark lanes, and innumerable faint suns that complicate detection and measurement. The geometry also keeps the object low for northern observers, making southern observatories the natural sentries for the first chapters of its story. The hyperbolic nature tells us something decisive about origin. A body that is flung outward by a planet can become unbound, but that ejection produces an outbound trajectory. Our visitor is inbound and already unbound before it feels serious planetary tugs. Its excess speed at infinity is positive, a quiet but undeniable signature of birth elsewhere. The path is steeply tilted with respect to the ecliptic, not lined up with the family lanes of our planets. Gravitational nudges from Jupiter and its kin will bend the track a little, but cannot turn a foreigner into a resident. Follow the curve forward, and the message is equally clear. After the swing at perihelion, the object climbs back toward the southern sky, and then outward beyond the realm of the giant planets, fading below the reach of even the largest mirrors. Project its motion far into the past, and it dissolves into the random drift of interstellar space. Too many stellar encounters ago to name a single cradle star. What remains is direction and dynamical class. A stranger from the south, carrying the stamp of a different sun, writing a clean hyperbolic line across our sky and continuing on. First comes the long slide toward the sun, a steady brightening that is more about geometry than drama. Through early and mid-autumn of the year 2025, the object sinks into the sun's neighborhood in the sky, where the glare defeats most attempts to follow it. This is the season of solar conjunction, when the elongation is small, and even large professional telescopes must wait for safer angles. Observers mark time, polish ephemerides, and watch the uncertainty shrink as the predicted path tightens night by night. Near the end of October, the traveler reaches perihelion, the moment of closest approach to the sun. Speed peaks, the coma responds to rising heat, and the subtle forces of solar radiation and outgassing do their quiet work on dust and gas. For many on Earth, this milestone happens behind the bright curtain of daylight. The comet is there, but the sun is in the way. Astronomers plan to catch it on both sides of this turning point, comparing the before and after to learn how fast the activity ramps and how the tail geometry reshapes itself. In November, the object begins to pull free of the solar glare. The elongation widens, Air grows dark enough for cameras to gather hours of photons, and the southern sky keeps the best vantage for a while. Amateur imagers with patient tracking may tease out the coma, while professional facilities turn spectrographs toward faint molecular lines. Phase angle effects will change the apparent brightness and the look of the tail, sometimes sharpening structures that were hidden when the sun was too close on the sky. By December, the motion carries the comet to its minimum distance from Earth, still comfortably distant on the scale of the solar system, roughly on the order of 1 3/4 astronomical units. That nearness is not near in any threatening sense, but it is near enough to help science. Angular size grows a little, features become easier to resolve, and nightly changes can be mapped in a way that tightens models of dust, release, and grain size. The best wide-field images often come in this window, when sky placement and distance both cooperate. As the year closes, the arc turns outward. Brightness ebbs with the square of distance, structures soften, and the comet yields itself back to the background of the Milky Way. What remains is a clean sequence of milestones: the slide into conjunction, the late October burn around the Sun, the November emergence, the December passage at minimum distance, and the long fade. Each step fixes a pin on the calendar and a lesson in the logbook, turning a transient visitor into a well-observed chapter in the story of interstellar debris. Safety is the quiet headline of this story. The visitor's path keeps it well away from Earth, with the closest separation in late December measured in astronomical units, not in lunar distances. Think of an astronomical unit as the span between Earth and the Sun. At minimum, it stays about 1 3/4 of that span from us, a gulf so wide that our world is never in the same lane. The geometry is reassuring: different planes, different longitudes, and no crossing point where a collision could be arranged by chance or by mischief of gravity. Impact monitoring centers treat such cases with steady routine. As additional observations refine the orbit, the uncertainty shrinks, and the projected corridor of motion narrows like a road seen from above. The outcome here is simple. The object remains unbound, cuts inside the orbit of the giant planets, and then departs, all while keeping a healthy buffer from Earth. On the standard hazard scales used by planetary defense teams, that combination of distance and predictability sits at the most peaceful end of the spectrum. Brightness is not danger, and a tail is not a threat. A comet's glow comes from sunlight reflecting off dust and from gas fluorescing in space. The tail is a veil so thin that a hand could not collect it. Even if the coma grows livelier near the Sun, the stream of particles remains a tenuous wind that poses no risk at Earth's distance. The same radiation pressure that sculpts the tail also helps carry dust away from the inner system, spreading it over regions where it disperses into the background population of harmless meteoric specks. Doomsday rumors thrive on ambiguity, so let us be exact in spirit, if not in decimals. This is not an incoming impactor. It is a passerby on a hyperbolic errand, separated from us by a vast and measurable gulf. The only thing it will strike is our curiosity. That is why astronomers speak of opportunity rather than alarm. From a safe distance we can read its spectrum, watch its changing shape, and learn how ice and dust behave when warmed by our star. The lesson is both comforting and profound. The universe can be dramatic without being dangerous. A textbook comet begins with a small, dark nucleus. It is a fragile body of ancient dust, bound with ices such as water, carbon dioxide, and carbon monoxide. The surface is charcoal black and riddled with cliffs, pits, and fractures that vent gas when warmed. Spin and sunlight drive that venting into jets, which loft grains from the surface and feed a temporary atmosphere around the core. This shroud is the coma, a luminous cloud that can swell to planetary size even though the nucleus itself is only a few kilometers across. From the coma grow two classic tails. The ion tail is made of gas molecules stripped of electrons by sunlight and herded by the solar wind along invisible magnetic fields. It points almost straight away from the sun like a taut ribbon. The dust tail is different. It is built from heavier grains pushed gently by radiation pressure and shaped by the comet's motion, so it bends into a graceful curve. Both tails are incredibly diffuse. Their glow is simply sunlight scattered by tiny particles, more like breath on cold air than a solid streamer through space. Activity rises and falls with distance from the sun. Far out, only the most volatile ices can sublimate, and the comet stays quiet. Closer in, water ice wakes, jets multiply, and the coma brightens while the nucleus may shed boulders or crack. Dust can settle back to form an insulating mantle that dims later returns. Pieces shed along the orbit become meteoroid streams that long after the comet has passed may brush Earth as gentle meteor showers. In this way, a comet is both a traveler and a storyteller, carrying the chemistry of its birthplace and revealing it through light, gas, and dust. An anti-tail looks like a cometary tail that breaks the rules. Instead of streaming away from the sun, a thin spike seems to point sunward, as if the comet were dragging a lance into the light. The effect is unsettling on first glance, because it appears to contradict the basic physics that shapes ordinary tails. But the anti-tail is not a reversal of the solar wind or a new force. It is an illusion of perspective produced when dust lies in a flat sheet near the comet's orbital plane, and our viewpoint lines up just right with that sheet. To understand it, imagine the comet leaving behind a road of dust grains as it travels. Radiation pressure pushes the finest grains strongly, curving them into the classic dust tail, while larger grains respond more slowly and remain closer to the orbital plane. When Earth crosses that plane, or when the alignment becomes very shallow, we look almost edge-on at the sheet of larger particles. Edge-on sheets look like needles. Because the sheet extends behind the comet along its orbit, the apparent needle can project toward the sun even though every grain still obeys sunlight's push. This is why astronomers speak of projection geometry. On the sky, we see a two-dimensional picture of a three-dimensional dance. The ion tail still points away from the sun, blue and linear, carried by the solar wind. The true dust tail still curls gently away, shaped by motion and light. The anti-tail appears when a third structure becomes briefly visible. The orbital plane sheet of slow, heavy grains, seen edge-on. It looks sunward only because the plane, not the particles, crosses the line between the comet and the sun from our vantage point. Classical models describe this behavior with families of curves called synchrones and syndines. Synchrones group particles shed at the same time. Syndines group particles of the same size. The anti-tail belongs to the territory where large-grain syndines hug the orbital plane. Under certain phase angles near plane crossing, the superposition of these curves collapses into a narrow spike. The spike brightens quickly because the sheet's surface brightness is concentrated by perspective, then fades as our sightline tilts away and the sheet opens back into a fan. Color and texture provide additional clues. Ion tails often glow with a cool tint and appear sharply filamented. Ordinary dust tails show a warmer, sunlit hue and a soft curvature. Anti-tails tend to be warmer still and narrower, almost pencil-thin, betraying their origin in larger, less mobile grains. They can also appear offset from the ion tail by a noticeable angle, underlining that three distinct structures may be present at once. A comet with an anti-tail can therefore look like a trident, a blue ray, a broad amber fan, and a skinny sunward spike. History reminds us that anti-tails are rare rather than impossible. The famous Roland comet of 1957 displayed a dramatic sunward spike that startled observers and helped cement the orbital plane explanation. Since then, several comets have offered shorter, subtler versions during brief windows of geometry. These episodes teach a practical lesson for skywatchers and modelers alike. Timing matters. The spectacle often lasts only days or a few weeks, around the moment when Earth's line of sight slices the dust sheet just so. For an interstellar visitor, the anti-tail feels stranger because we do not know the dust recipe. Grain sizes, shapes, and cohesion reflect the conditions of a distant nursery, and the very first heat of our sun may release particles in proportions unlike those of comets born here. If the object sheds a relatively heavy population of larger grains, the orbital sheet becomes well populated, and the anti-tail sharpens. That is not a sign of engines or intention. It is a map of particle physics written in sunlight, projection, and motion. Thus, the anti-tail is a paradox only in appearance. Every grain still arcs away under radiation pressure. Every ray still respects the sun. What changes is our angle. When geometry compresses a dusty plane into a line, we witness a comet violate our intuition without violating the laws of nature. In that brief alignment, the traveler seems to point back toward the fire it is fleeing, like a shadow that leans the wrong way at dusk. Then, the angle loosens, the needle dissolves into a fan, and the sky returns to its familiar grammar. As the traveler descends toward perihelion, sunlight awakens different layers of ice in sequence. First, the more volatile compounds stir, then water begins to flow, and the coma swells as jets entrain dust from caverns and scarps. Outgassing is not a steady faucet. It is a set of pulses governed by spin, topography, and thermal inertia. One face of the nucleus may roar while another stays hushed, so the apparent brightness flickers from night to night. Radiation pressure then sorts the newly freed grains by size, carving threads, fans, and shells that redraw the comet's outline in a matter of days. Morphology responds to this breathing engine with almost biological restlessness. A narrow jet can curl into a spiral as the nucleus turns. A broad fan can split into layered sheets when grain sizes separate. Discrete clumps can shear into striae that trace the flow of light and motion. When activity surges, the inner coma turns grainy and structured. When it ebbs, the same region relaxes into a soft haze. Small changes in the phase angle can amplify or mute these patterns, so a comet may appear to grow a new organ overnight, when in fact the line of sight has simply shifted across a three-dimensional plume. Compared with the second interstellar visitor, known as Borisov, this object seems more mercurial. Borisov behaved like a textbook comet sculpted by ancient cold, with outgassing dominated by familiar ices and a relatively steady production curve. Our present guest hints at a dust budget skewed toward larger grains and a cocktail of volatiles that wakes early, which together sharpen the jets and quicken their evolution. None of this suggests artifice. It reflects geology, spin, and sunlight playing across material forged under a different star, a natural laboratory where variability is the very signal we came to read. Rumor loves a mystery, and a sunward spike or a curious spectral line can sound like a message rather than a measurement. In the rush of headlines, an anti-tail becomes a thruster, a flicker becomes a beacon, and an interstellar comet becomes a vehicle with intent. But observation is not narrative. What astronomers have in hand are images, time series, and spectra, each with uncertainties that are written down and shared. A sunward needle is a plane of dust viewed edge-on. A bright or dim night is a change in geometry or outgassing, not a coded signal. The sky is speaking physics, not plot. Overinterpretation thrives on selective framing. A cropped image hides the ordinary tails that accompany the narrow spike. A single spectral bump is quoted without the context of signal-to-noise or competing identifications. Vocabulary drifts, and soon candidate reads like confirmed and may indicate hardens into proves. The scientific process pushes the other way. Teams post preliminary reductions, invite replication, and mark error bars in sober type. Claims that survive this mill of critique gain weight not because they are exciting, but because they are durable against doubt. Extraordinary ideas are not forbidden. They are simply required to pay in evidence. Does the claim rest on a reproducible feature seen by independent instruments? Are calibration files public? Do models predict the same feature under reasonable assumptions about dust size, temperature, and viewing angle? Reliable sources tend to answer with data, methods, and caveats. Space agencies, major observatories, and peer-reviewed journals practice that discipline. They may sound less thrilling than a viral thread, yet they are the places where surprises, when real, are carefully uncovered rather than casually declared. For the rest of us, a few habits guard against the drift from wonder to fantasy. Compare multiple reports rather than a single loud voice. Look for the words that scientists actually use: uncertainty, confidence, alternative explanations. Notice when an explanation accounts for many details at once, as the orbital plane dust sheet does for the anti-tail, versus when a story leans on intention or agency without mechanism. Curiosity is the right response to a stranger from the stars. Credulity is not. If we keep that distinction, the comet will teach us more than any rumor ever could. Spectroscopic observation is the art of taking light apart to learn what made it. A prism or a diffraction grating spreads a comet's glow into a rainbow where certain colors are missing or unusually bright. Those patterns are not decoration. They are fingerprints of atoms and molecules. When a cool gas sits in front of a source of light, it swallows very specific colors and leaves thin, dark absorption lines. When a tenuous gas is excited, it shines at those same specific colors and draws bright emission lines. Each element speaks its own set of lines, as distinctive as a voice. For a comet, this matters because the nucleus is small and hidden, while the surrounding coma and tails are made of sunlight, gas, and dust. A spectrograph lets astronomers separate the gentle continuum glow of dust from the sharp lines of gas. In those lines, they can recognize the breath of water, the signature of carbon monoxide, the telltale bands of carbon dioxide in the infrared, and the violet light of cyanogen. They calibrate carefully with lamps and skylines, remove instrumental effects, and then compare the measured pattern with laboratory standards to identify what is present. The The strengths and shapes of the lines carry deeper clues. Ratios between lines reveal temperature and density. The spread of a line in color can show the speed of outflowing gas. As molecules break apart in sunlight, daughter species appear, allowing teams to trace the chemical family tree from parent ices to fragments. With repeated spectra over many nights, one can watch jets switch on and off, estimate production rates of gas and dust, and map how activity responds to the sun. In this way, spectroscopy turns a faint smudge into a story about chemistry, motion, and heat. Spectra from the Hubble Space Telescope, the James Webb Space Telescope, and leading ground observatories sketch a chemistry that does not feel entirely familiar. The rainbow of the comet is threaded with bright bands that point to abundant carbon dioxide, joined by water and a quieter but steady breath of carbon monoxide. Cyanogen paints its violet signature in the optical, a classic cometary tracer that helps separate dust glow from gaslight. Taken together, these lines say the coma is lively and layered, with different families of molecules waking at different temperatures as sunlight rises. What stands out first is the balance between carbon dioxide and water. In many comets that were born here, water claims center stage once the sun's warmth is strong, while carbon dioxide plays a supporting role farther out. This visitor tilts the script. The bands that belong to carbon dioxide appear unusually strong, suggesting that pockets rich in this volatile are close to the surface or are easily tapped by small fractures. That balance can shape the jet anatomy, because carbon dioxide sublimates at colder temperatures and can lead the surge before water fully joins. The carbon monoxide lines carry another clue. Carbon monoxide is even more volatile than carbon dioxide, and in some comets, it whispers rather than sings. Here, it is present enough to be heard clearly, hinting that parts of the nucleus are pristine or that the warming has reached reservoirs not yet depleted by countless past passages. Since this traveler is not a frequent visitor to our sun, its chemistry may preserve the imprint of a distant nursery, where temperatures and pressures wrote a different recipe into the ice. Cyanogen adds contrast in the visible, often blooming as a daughter product when sunlight breaks down more complex parents. Its emission helps astronomers map the interface between gas and dust. By comparing the strength of cyanogen with the glow from dust, teams can estimate how dusty or gassy the coma is at a given time and place. That ratio matters because it influences how sunlight sculpts the tail, how fast grains are lofted, and how quickly the comet's face changes texture as it turns and breathes. Across repeated nights, the line ratios shift in telling ways. When carbon dioxide leads, jets can flare at greater distance from the sun, and the dust sheet may thicken with larger grains that are dragged along by vigorous flows. When water catches up, the spectrum warms, and new structures appear close to the nucleus. Watching those handoffs is like eavesdropping on the comet's weather. The cadence of rise and fade reveals spin, shadowed caverns, and the thermal inertia of crust and mantle, all without ever seeing the small dark core itself. Compared with many hometown comets, this chemical portrait looks skewed toward the cold-born volatiles. That does not make the object alien in the sensational sense. It makes it informative. Composition is a fossil record written in ice. A comet that carries more carbon dioxide and a measurable share of carbon monoxide tells us about grains that formed farther from a young star, about mixing in a protoplanetary disk, and about the paths small worlds take before they are thrown into interstellar exile. In that way, the brightest lines in the spectrum are also signposts to another birthplace. Metal in a comet's breath sounds like a paradox. We imagine ices and dust, not the vapor of a forge. Yet high-resolution spectra sometimes reveal hair-thin emission lines that belong to neutral nickel, a whisper of metal atoms drifting through the coma. These lines are faint but orderly, appearing at precise colors set by quantum rules. Their very presence suggests that a few atoms of nickel are being released from grains or molecules into the gas around the nucleus, even though the environment is cold by earthly standards. How can nickel escape in such gentle warmth? One idea is that sunlight liberates atoms from the surface of dust by a process called photodesorption, a kind of molecular nudge that shakes loose weakly bound species. Another envisions fragile parent molecules that carry nickel in a volatile cage, which breaks apart under light and gifts the atom to space. There is also the slow sputtering of grains as they collide or are eroded by radiation and micro-impacts. None of these mechanisms requires a furnace. They depend instead on time, light, and very low densities. The lines themselves offer clues beyond their mere existence. Their sharpness tells us the atoms are not in violent motion, while their relative strengths hint at how many are present and how they are excited. If the nickel lines rise and fall with specific jets, that points to localized sources on the nucleus, perhaps cliffs or fractures where fresh material is exposed. If they track the overall coma, the source may be a widespread population of grains slowly releasing atoms as they are heated and turned by sunlight. Comparisons with iron are especially interesting. In some comets, the nickel-to-iron balance appears unexpectedly high in the gas, even though solid grains in meteorites can favor iron. That mismatch hints at a chemical sieve. Nickel may hide in compounds or surface sites that free it more readily than iron under gentle heating and ultraviolet light. Grain size matters too. Larger, older grains can shelter iron deeper within, while nickel near the surface leaves earlier, tipping the gaseous ratio without changing the bulk rock itself. For an interstellar visitor, the stakes are higher because composition is a story about birthplace. If nickel lines persist at large distances from the Sun, they may signal very volatile carriers or unusually accessible grain coatings formed in a cold, shadowed nursery. If the lines flare only near perihelion, they may reflect late-stage processing as the crust fractures and reveals new pockets of material. Watching the timing, pairing spectra with images of jets, and tracking changes across a rotation can turn those faint lines into a map of the nucleus. Caution belongs beside excitement. The features are subtle, the background crowded, and identifications must survive independent reductions, different instruments, and careful calibration. Still, if the nickel signature holds, it becomes a powerful tracer. It tells us which grains respond first to sunlight, how quickly metals move from solid to gas, and how an alien small world weaves dust, ice, and trace atoms into a living coma. In that sense, the nickel lines are not decoration. They are the quiet handwriting of geology in space. Each observing day is really a dance between angle and light. The comet shares the sky with the Sun, so the key number is the elongation, the apparent separation on the dome. When that angle is small, the glare wins and the object drowns in blue daylight. When it widens, darkness returns and the comet steps out. Twilight becomes your clock. Civil twilight is still washed with glow, Nautical twilight is a dim shoreline of color, and astronomical twilight brings the true black, needed for long exposures and for teasing structure from a faint coma. Around the period of solar conjunction in mid-autumn, the comet sidles too close to the sun for comfortable work. Professional safety rules forbid pointing major mirrors near the limb, and even for amateurs, the risk of stray sunlight is not worth a heroic attempt. This is the waiting room of the campaign. You keep refining ephemerides, weigh the last usable frames from the previous week, and plan the first after-conjunction runs. The sky will open again, first as a narrow window at the horizon, then as a generous span of dark hours. After the swing at closest approach to the sun, the daily window begins to widen. On some evenings, the comet will sit low after dusk, arcing down to the horizon before midnight. On other dates, the geometry favors the pre-dawn sky, where it rises ahead of the sun and offers a calm hour of darkness before the first whitening of the east. The rule is simple: chase elongation. A few degrees gained can turn a frustrating half hour into a productive session long enough for deep stacks and for spectra with real signal. The southern hemisphere enjoys the earlier advantage in placement, with the comet tracking through rich star fields where the Milky Way complicates background subtraction but rewards wide-field frames. Northern observers see improving chances as the season advances and the object climbs to kinder altitudes. In both hemispheres, low altitude means thicker air and restless seeing, so shorter sub-exposures stitched into a stack often beat a single long shot. Stable mounts, careful polar alignment, and patient guiding pay dividends every clear night. Moonlight is the other tide that shapes the window. A bright moon erases faint contrast and hides the outer coma. A dark moon unlocks delicate shells and jets. Plan your week around that rhythm. Use bright moon nights to refine pointing, framing, and calibrations, then spend the dark run gathering the science frames that reveal dust textures and gas structure. Phase angle matters as well. Forward scattering can give the comet a brief, mischievous boost, while a larger angle may emphasize the ion tail. Either way, the clock is geometry, not luck. From a practical standpoint, treat each night like a field campaign. Check the latest coordinates from a trusted ephemeris, print a finder chart, and sketch an image sequence that brackets exposure times. Never gamble with the sun. Observe only when it is safely below the horizon, and keep hard limits on elevation. If clouds steal the show, log what you attempted and why, because the habit of notes becomes tomorrow's clarity. Day by day, the observing window grows, breathes, and recedes. Ride that breathing, and the comet will give up its secrets. The Hubble Space Telescope provides sharp vision in visible and ultraviolet light, measuring the shape of the inner coma and tracing fine jets that would otherwise blur together. Its stable platform and precisely known instruments make it the anchor for morphology. When the comet skirts crowded star fields, Hubble's resolution separates the visitor from the glitter of the Milky Way and turns a soft glow into a map of structures that evolve from night to night. The James Webb Space Telescope listens in the infrared, where ices speak clearly. Webb's spectrographs spread the comet's light into bands that reveal water, carbon dioxide, carbon monoxide, and the faint signatures of more complex species. Thermal emission from dust becomes a thermometer, telling how grains warm and cool as the object turns. Webb can follow the handoff between volatiles as the sun's heat rises, showing which gases lead, which lag, and how that choreography sculpts the jets that feed the tails. On the ground, the big mirrors take shifts. Keck on Mauna Kea brings high-resolution spectroscopy in the optical, catching narrow lines from gas and faint tracers that hint at metals. The twin Gemini telescopes add flexible imaging and rapid response, switching filters to build time series that track changes across a single night. In the Atacama Desert, the Very Large Telescope pairs sharp seeing with powerful spectrographs, turning the southern sky into a laboratory where geometry, dust size, and gas flow can be untangled with patient exposure. Survey systems keep the wide view. The Asteroid Terrestrial Impact. Last alert system that first flagged the moving dot continues to harvest positions, shrinking orbital uncertainty and guiding the heavy hitters. The Zwicky Transient Facility and other patrols stitch together light curves that reveal rotation and activity cycles. When the comet strays too close to the sun on the sky, heliophysics spacecraft with coronagraphs can sometimes catch it at the edge of daylight, extending coverage through the tightest parts of the geometry. Across both hemispheres, university telescopes and dedicated amateur networks fill the cadence. Small and medium apertures can watch more often, building nightly mosaics that large observatories cannot afford. Coordinated campaigns share finder charts, exposure recipes, and calibration frames so that data from many apertures add up cleanly. The Minor Planet Center collects the astrometry that keeps everyone pointed true. In this way, a single visitor becomes a chorus of instruments and eyes, each adding a register to the music of dust, gas, and light. The first objective is to measure how dust and gas couple near perihelion. As sunlight rises, different ices wake in sequence and jets begin to sculpt the coma. By combining imaging and spectroscopy, teams will track how gas production drives dust lifting, how fast grains accelerate, and how quickly structures respond as the nucleus turns. Models of flow will be tested against real-time changes, seeking the thresholds where gentle sublimation becomes a burst, and where a localized vent grows into a fan that feeds the larger tails. A second objective is to map the distribution of particle sizes. Grain size leaves signatures in brightness, in polarization, and in how sharply the dust tail bends. By comparing observations taken at small and large phase angles, astronomers can separate fine smoke like particles from heavier, slower grains. The goal is to turn curves on the sky into physical histograms of grain sizes, and to learn whether this traveler carries a dust recipe different from comets born under our sun, with consequences for color, texture, and the efficiency of light scattering. The third objective focuses on the anti-tail and its variability. If the sunward spike is the edge of a dust sheet that lies in the orbital plane, its appearance should strengthen and fade with geometry, and its brightness should track the supply of larger grains. Teams will follow that needle through the weeks around plane crossing, measuring its width, length, and offset from the ion tail. The result will test synchrones and syndynes in a live setting and reveal whether the sheet is built by steady shedding or by episodic releases tied to rotation and terrain. A fourth objective is to read composition as a function of distance from the sun. Infrared spectra will watch the handoff between carbon dioxide, water, and carbon monoxide, while optical spectra trace cyanogen and faint metal lines. By repeating these measurements before and after perihelion, astronomers can build production curves for each species and ask which ices lead, which lag, and whether trace metals like nickel appear early through delicate surface processes, or only later when crusts fracture. This time series turns chemistry into a clock and a thermometer. Finally, the campaign aims to fold these strands into constraints on the nucleus itself. Light curves and jet periodicities can refine the rotation state. Coma brightness and gas output can bound the size and albedo. The mix of grains can hint at layering, porosity, and the strength of surface mantles. Together, these targets sharpen a larger question. How does a small world forged under a distant star react to the first serious warmth of our own? By answering it with patient, quantitative work, we turn a passing spectacle into comparative planetology. For most backyard observers, the practical window opens after the comet clears the sun's glare in late 2025 and widens through early 2026. The first good chances favor the southern hemisphere, where the object sits higher against rich Milky Way fields. As weeks pass, northern latitudes gain ground, and the arc climbs to kinder angles. Think in terms of safe elongation and true darkness. Wait until astronomical twilight has ended, keep the sun well below the horizon, and choose nights when the moon is thin or absent, so faint contrast can breathe. Expect a challenge suited to patient imagers. Large amateur telescopes help, but modern cameras and careful technique matter just as much. Treat the comet like a very low surface brightness galaxy. Use many short exposures to tame unsteady air, then stack them to reveal the coma and any delicate structures. A sturdy equatorial mount, thoughtful polar alignment, and gentle guiding will reward you. If your skies glow with city light, try a darker site or shoot near the meridian, where the air is thinnest along your line of sight. Finder charts and up-to-date ephemerides are your compass. Check a trusted sky service on the afternoon of each attempt, print the star hop, and annotate it with field of view boxes for both the telephoto lens and your telescope's main camera. Because the comet's brightness will depend on geometry, activity, and phase angle, be ready for nights when it looks shy, and others when a dust fan or a narrow spike seems to sharpen. Do not chase miracles, chase cadence. A consistent series separated by a day or two will tell a richer story than a single heroic session. Visual observers with dark skies may glimpse a diffuse glow in larger instruments when conditions peak, but photography will carry most of the burden. Use gentle stretching and processing. Avoid aggressive noise reduction that erases real texture, and compare your frames to star catalogs to guard against wishful thinking. Above all, observe safely. Never point near the sun, even in daytime tests, and set hard elevation limits to avoid stray light. With patience through late 2025 and the first months of 2026, the stranger from between the stars will yield itself to careful eyes. Three, I-Atlas matters because it enlarges the small but growing census of interstellar wanderers. With only a handful of known examples, each newcomer reshapes the averages, sizes, surface colors, dust recipes, and the balance of ices that wake under sunlight. Where the first visitor behaved like a geometric riddle and the second resembled a classical comet, this traveler seems chemically and morphologically skewed toward colder-born volatiles and larger grains. Adding a third data point turns anecdotes into trends, letting astronomers ask population questions instead of retelling a single strange tale. Its path through space also anchors models that connect our solar system to the broader galaxy. A clean hyperbolic trajectory arriving from southern skies helps chart the directions from which such objects tend to come, testing ideas about the solar apex and about how stars and their debris move relative to our own. If interstellar visitors prefer certain lanes, that pattern may reflect the churn of planetary systems and the gravitational traffic of giant worlds that fling small bodies outward. 3I Atlas is therefore not just a curiosity, it is a compass needle in galactic kinematics. Chemistry makes the case even stronger. Spectra that emphasize carbon dioxide, register a steady breath of carbon monoxide, and hint at trace metals turn the comet into a portable core sample from a foreign nursery. Those clues let researchers infer temperatures, pressures, and mixing in a distant protoplanetary disk where its building blocks formed. By comparing the timing of gas release, the grain size distribution, and any sunward dust sheet with well-studied comets born here, we can separate what is universal in comet physics from what is local to our own planetary neighborhood. Finally, 3I Atlas advances the craft of discovery itself. It mobilizes a global relay of surveys, space telescopes, and patient amateurs, sharpening methods for rapid orbit determination, coordinated spectroscopy, and safe observing near the sun's glare. It also strengthens the public habit of weighing evidence over rumor, because a high-profile interstellar visitor invites both wonder and exaggeration. When the data win, we gain twice: new knowledge about how small worlds are made beneath other suns, and a clearer, steadier way of listening to the sky when the next stranger arrives. Interstellar comets are postcards from other workshops of creation. The gases and dust they release are not random exhaust. They are samples of the pantry from which their home worlds were baked. When carbon dioxide wakes before water, or when carbon monoxide persists far from the sun, we glimpse a nursery that was colder, darker, or more gently heated than ours. Grain sizes tell more. Coarse, slow-moving dust points to growth and sticking in calm regions of a protoplanetary disk, while fine smoke like particles hint at fragmentation or fresh surface frost. Each trait is a clue to conditions we cannot visit. These clues connect directly to what telescopes see in young stellar disks. Infrared spectra of the comet can be set beside ringed disks mapped in radio light, where ice lines divide warm inner zones from cold outer shelves. If an interstellar visitor carries an abundance of volatiles that form beyond a certain frost line, it argues for efficient mixing that ferried those ices inward, or for planet embryos that stirred the disk like spoons and blasted pebbles outward. In this way, a faint comet tail becomes evidence in the larger trial about how planets migrate and how their raw ingredients are shuffled. Even dynamics whisper about the parent system. A clean hyperbolic arrival tells us the body was thrown out, most likely by a giant planet trading energy during a long courtship of weak encounters. The angle of approach and the excess speed at infinity, paired with the comet's chemistry, let modelers ask what kind of planetary architecture did the tossing. Was it a single hefty world acting like a slingshot, or a family of migrating giants sweeping resonances across the disk and emptying vast swaths of small bodies into interstellar space? The answer sketches silhouettes of unseen planets. Finally, diversity itself is the message. With each visitor, we test whether certain chemical ratios recur, whether dust textures follow familiar patterns, and whether metal vapors appear under similar warmth. Repetition hints at universals in planet building. Departures highlight the freedom of other suns to write their own recipes. 3. Eye-Atlas thus serves as both specimen and mirror. It shows us what can happen elsewhere and sharpens what we know about home, turning a brief passage through our sky into a long conversation about how worlds are made across the galaxy. Just Got Stranger is not a promise of shock for shock's sake. It is a measure of how far this traveler has nudged our expectations. We thought we knew the grammar of comets, gas and dust streaming away from the sun, gentle curves that trace familiar physics. Then a sunward needle appeared, a seeming defiance that is really a trick of alignment, a dust sheet seen edge on. The sky has not broken its rules. It has asked us to revise the picture we carried in our heads. Stranger means the map was too simple, and the view is now richer. Stranger also lives in chemistry. The spectrum does not arrange itself exactly as our local comets often do. Carbon dioxide speaks early and with force. Carbon monoxide keeps a steady whisper. Cyanogen paints the visible with delicate lines, and there may be the faint handwriting of metals in the coma. None of this proves an exotic engine. It suggests a recipe mixed in colder aisles of a distant disk, a pantry of ices and grains that awakens under our sun in a sequence we did not predict. The unfamiliar balance is not noise, it is information. There is a third layer to the word. The calendar itself has become part of the story. The comet dives toward the sun, slips into conjunction, and then steps back into darkness. Around perihelion, sunlight presses, jets breathe, and shape transforms on human timescales. The most telling spectra and the sharpest images often arrive just after this turn. To say, "Just got stranger," is to invite patience, to ask viewers to stay with the data through the awkward weeks when geometry hides the stage and then, suddenly, reveals it. Stranger does not mean unsafe. The path misses Earth by a broad and measurable gulf. What it threatens is our complacency. An anti-tail that points sunward, a volatile lead that challenges the usual order, a whisper of metal where few expected it. Each detail pulls on a loose thread in our assumptions. The wonder here is how quickly careful work can turn spectacle into understanding. When we let perspective, composition, and timing speak together, the contradictions soften into a coherent portrait of dust, ice, light, and motion. There is a responsibility that comes with that word. In an age of quick takes, strangeness is easily traded for fantasy. This film has tried to separate rumor from result, to keep provisional claims marked as provisional, and to celebrate doubt as the tool that refines discovery. The comet asks for the same discipline from all of us. Compare sources, watch the error bars, notice when an explanation accounts for many details at once. Let surprise survive, but do not let it drift into story without evidence. If there is a moral, it is that strangeness is how nature teaches. With each interstellar visitor, the universe adds a new accent to a language we are still learning. Some patterns repeat and become rules, others refuse to fit and become questions. 3 lessons stand out here. Geometry can deceive and must be modeled. Chemistry can invert the order we expect, and the best truths arrive on a schedule set by the sky, not by our impatience. Hold those lessons, and the next stranger will feel a little less strange. So when we say, just got stranger, we mean that a threshold has been crossed. We began with a headline about a visitor from between the stars. We end with a set of precise puzzles that will be tested as post-perihelion data arrive. The evolution of the sunward dust sheet, the handoff among volatiles, the fate of trace metal lines as the nucleus turns and cools. Stay with the evidence. The reward for patience is not merely an answer, it is a deeper